Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module X-ray production from the paper Measurements and Instrumentation. From this module, students may get to know about the following topics. First, we will learn about the X-ray production both by laboratory source and synchrotron sources. Main components of the X-ray tube will be discussed. Characteristic and Bremsstrahlung radiation will be detailed. X-ray radiation from synchrotron sources will be studied. Major components of X-ray beamline will be discussed, and towards the end, goniometers used for X-ray measurements will be discussed. Discovery of X-rays was done by the German physicist Roentgen in the year 1895. The nature of X-rays so discovered was unknown at that time, and hence they were named as X-rays. The exact nature of these X-rays was finally established in the year 1912. The phenomenon of X-ray diffraction by crystalline solids was discovered in this particular year. The discovery of X-ray diffraction proved the wave nature of X-rays. Thus, a new method for examination of the fine structure of matter was made known. X-ray diffraction is extremely useful technique as it is capable to indirectly reveal details of the internal structure of matter up to the order of 10 raised to minus 8 centimeter in size, which is angstroms order. The nature of X-rays is basically same as light and are electromagnetic radiation, but their wavelength is very much shorter. In the X-ray region, the unit of measurement used is angstroms. For X-ray diffraction measurements, the X-rays are used having wavelengths lying approximately in the range of 0.5 to 2.5 angstroms, which is very small as compared to the wavelength of visible light, which is of the order of 4,500 angstroms to 6,000 angstroms. Thus, X-rays fall in the electromagnetic spectrum in the region between gamma and ultraviolet rays. Till the mid-1970s, X-ray tubes were only used as X-ray sources, in which X-rays are generated by bombarding high-energy electrons on a suitable target like copper or molybdenum. Then, later it was observed that the synchrotron radiation emitted from the circulating charged particles was possible, and it was much more powerful and adaptable source of X-rays. The charged particles circulate in the storage rings, which were initially constructed for high-energy nuclear physics experiments. Today, synchrotrons have indeed proved to be such enormously improved source of X-rays that many storage rings have been erected around the world, devoted exclusively for the production of X-rays. So students, let us first study about the laboratory source for the production of X-rays. After the discovery of X-rays in 1985, the first X-ray tube to be used as a standard X-ray source was developed by W. D. Coolidge in 1912. A typical X-ray tube consists of a filament or cathode made of tungsten to produce electrons which are focused and accelerated by applying a high voltage between cathode and anode. The anode is generally coated with a metal like copper, molybdenum, etc., depending upon the requirement of wavelength of X-rays to be generated. The point where the electron beam strikes the anode is called the focal spot. Most of the kinetic energy of electrons after bombardment with anode is converted to heat, and only about 1% of the energy is converted to X-ray. The heat generated during the bombardment is dissipated by keeping the anode in contact with circulating coolant like cold water. This generation of heat at anode and efficiency of cooling restrict the power of the X-ray tube around 1 kilowatt. A further improvement in the power was achieved when a rotating anode was used instead of fixed anode. A rotating anode can dissipate heat over a larger volume compared to fixed one. The technical difficulties like problem of maintaining high vacuum seal on the rotating shaft of anode took some time to settle, and only after 1960s rotating anode X-ray sources could be available on commercial basis. X-rays produced from bombardment of electrons on anode consist of two distinct components depending on the nature of interaction of electrons with anode material. A part of it consists of continuous X-rays, which is obtained due to the deceleration of electrons, which are eventually stopped in the metal. This is known as Bremsstrahlung radiation and has maximum energy that corresponds to the high voltage applied to the tube. During collision of a high energy electron with an atom of the anode, an electron from inner shells of the atom can be knocked by making a vacancy. The spontaneous transition of an electron from an exterior shell into the vacancy generates an X-ray photon with a characteristic energy which is equal to the difference between the energies of the shells. These characteristic energy peaks superimposed on continuous Bremsstrahlung give the total spectrum of X-rays emitted from that particular anode material. The experiments with monochromatic beam utilize the K lines of the anode material, which is numerous orders of magnitude more intense than Bremsstrahlung spectrum. The figure shows the X-ray spectrum from a anode material, showing a continuous Bremsstrahlung radiation in the background and characteristic X-ray peaks K alpha and K beta, as is shown clearly. It first of all consists of the generation of electrons, which is then passed in the LINAC, where the electron is given high energy, which feeds the electrons to the booster ring and then finally to the storage ring. Due to the deceleration of electron at every moment when it is changing its path of direction, the X-rays are emitted, and these X-rays are then passed on to the monochromator and after that onto the focusing devices and finally on the spectrometer, where the X-ray diffraction experiments or the X-ray scattering experiments will be performed. The details of a synchrotron source will vary according to the specific requirements, but several constituents will be present in one form or the other. Synchrotron light starts with an electron gun. A heated element or cathode yields free electrons which are pulled in a hole towards the end of the gun by a powerful electric field, which produces an electron stream. The stream of electrons is fed into a linear accelerator or LINAC. Here, the stream of electrons is chopped into bunches or pulses by high energy microwaves and radio waves. When they exit the LINAC, the electrons are traveling at 99.99986% of the speed of light and consist of about 300 million electrons. The stream of electrons from LINAC is fed into the booster ring. Magnetic fields are created in the booster ring in order to force electrons to move in a circular orbit. In this process, the energy in the electron stream is ramped up to the order of giga electron volts, that is GeV, inside the booster ring. This much energy of electron stream is sufficient enough to yield synchrotron light in the range of infrared to hard X-rays. The electrons are then fed from the booster ring to the storage ring, which is a many-sided donut-shaped tube. The storage ring is maintained under vacuum and is tried to be kept as free as possible of air or other stray atoms that could deflect the electron beam. Bending magnets or insertion devices such as undulators are used to finally produce the synchrotron light. Bending magnets deflect the electron beam to produce the radiation. The main function of bending magnets is to bend the electrons into their racetrack orbit. A bunch of X-rays is emitted tangentially to the plane of the electron beam. As the electrons pass through these bending magnets, deflecting electrons from their straight path. The obtained synchrotron light from the bending magnet consists of a wide and continuous spectrum in the EM chart and covers the range from microwaves to hard X-rays. The synchrotron light from the bending is much less brilliant or focused as compared to the finer beam of X-rays obtained from an insertion device. Insertion devices consist of magnetic structures called undulators, which are made up of small magnets arranged in a complex array. The structure of undulators is such that it forces the electrons to track an undulating or wavy flight. The radiation emitted at each consecutive band overlaps and interferes with that from other bands. This produces a much more focused or brilliant beam of X-ray radiation than that produced by a single magnet. Further, the photons so emitted are concentrated at certain energies, which are called as fundamental or harmonics. The wavelength of X-rays can be fine-tuned by changing the gap between the rows of magnets. The second key component in the synchrotron sources is the monochromator, which is used to select a particular wavelength required for many applications. The monochromators are generally made up of perfect crystals or of epitaxial multilayers and thus allow for considerable variation in the parameters, which may be desirable to choose the wavelength bandwidth. After this, the monochromatic beam is focused down to small sizes by using special devices such as refractive Fresnel lenses and X-ray mirrors. Finally, X-rays are transported to the sample on which experiments are performed. The quality of the synchrotron X-ray beam can be parameterized depending upon several aspects. These aspects can be combined into single factor called as brilliance. First of all, there is a number of photons emitted per second. Then, collimation, which defines how much beam diverges as it propagates. Collimation is in milliradians, both in horizontal and vertical directions. Other important aspect is the source area, which is given in millimeter square. Lastly, important factor is the spectral distribution. Some sources produce very smooth spectra, others have peaks at certain photon energies. The convention is therefore to define the photon energy range as a fixed relative energy bandwidth, which is chosen to be 0.1%. Altogether, the figure of merit of the source is given as brilliance, which is equal to photons per second divided by milliradian square, millimeter square source area multiplied by 0.1% bandwidth. The brilliance is a function of the photon energy. The maximum brilliance from third generation undulators is approximately 10 orders of magnitude higher than that from a rotating anode copper K-alpha line. So students, now let us see the main components of a beamline present at the synchrotron sources. A standard synchrotron beamline consists of the following components. First, the monochromator. For X-rays, silicon or germanium single crystals are used as monochromators. The purpose of these single crystals is to extract a particular wavelength or energy from the white X-ray beam. This is done by incidenting the white beam on the crystals, and the lattice planes of the crystals diffract the X-rays of different energies in different directions in accordance with the Bragg's law. In order to direct the diffracted beam in the same direction as the incident one, another similar crystal parallel to the first is used, as is shown in the figure. Monochromators with this kind of crystal arrangement are known to be double crystal monochromators. The figure shows the schematic of the double crystal monochromator. The various other components of a standard synchrotron beamline are as follows. Second component is the windows. Thin sheets of metal, often beryllium, which transmit almost all of the beam but protect the vacuum within the storage ring from contamination, are generally used as windows. Third component are the slits. In order to define both the horizontal and vertical beam size, several slits are used before indenting the beam on a sample of interest. Fourth component is the focusing mirrors. One or more mirrors, which may be flat, bent flat, or toroidal, are used to collimate or focus the X-ray beam. Lenses may also be used as focusing mirrors. Fifth component is the spacing tubes. Vacuum tubes which provide the proper space between optical elements and shield any scattered radiation are generally used in beam lines. Now students, let us see a basic goniometer which is used for the X-ray scattering measurements. For the X-ray scattering measurements from solid surfaces, the samples are vertically mounted on a triple axis goniometer head. Both translational and angular movements are possible using different stepper motors of the goniometer. As the direction of incoming X-ray beam is fixed, the angle of incidence theta I on the sample is controlled by changing the angle of the goniometer head with respect to the beam direction. The scattered beam is collected by the detector mounted on the 2 theta arm of the goniometer. Both the theta and 2 theta motors are mounted coaxially. The typical distance of monochromator to goniometer center and from this center to the detector is of the order of 40 centimeters for a lab goniometer. Movements of the goniometer are indicated in the figure. As shown in the figure, the goniometer is equipped with Z-motor to control translational movements along Z-axis, the theta x and theta y motors for rotations along x-axis and y-axis respectively. Apart from this, another phi motor about z-axis. There are separate microprocessors for all the theta to theta and phi movements, and also motor movements can be controlled from the control panel. While performing experiments on X-ray scattering, from the experimental point of view, it is extremely important to have precise machinery in order to have an accurate control over the incidence and exit angles. Also, X-ray sources are required which have low angular divergence. Today, both of these requirements are met easily due to the availability of very high precision diffractometers and the synchrotron radiation sources. So students, let us summarize what we have learned in this module. We learned about the X-ray production both by laboratory source and synchrotron sources. We studied that a typical X-ray tube consists of a filament or cathode made of tungsten to produce electrons which are focused and accelerated by applying a high voltage between cathode and anode. The anode is generally coated with a metal like copper or molybdenum, depending upon the requirement of wavelength of X-rays to be generated. We have also discussed the characteristic and Bremsstrahlung radiation from the laboratory X-ray sources. X-ray radiation from synchrotron sources has also been studied. We have also discussed in detail the major components of X-ray beamline, which consisted of detailed discussion over monochromators, windows, slits, focusing mirrors, and spacing tubes. Towards the end, goniometers used for X-ray measurements were discussed.